guys, and welcome. So today we're going to be talking about how to solve inequalities using induction, which we talked about in the previous episode. So, well, we can use induction not only to prove equality relations in algebraic kind of problems, but we can also do the same thing for inequalities. So let me guys to illustrate this concept to you on examples. So we would like to solve this particular problem. We would like to prove that n factorial is greater than or equal to the power of n for all n's that are greater or equal to 4 and natural. Awesome. So what I'd like to do is, first of all, I would like to achieve the base case scenario for this problem. So the base case right over there. So what is the first element in the set we are trying to operate on? Well, that's n is equal to 4. So the base case is also going to be n being equal to 4. Awesome. So for n equal to 4, what we get is, well, 4 factorial, which is equal to 24, which is 2 times 3 times 4, which is supposed to be greater than or equal to 2 to the power of 4, which is equal to 16. Well, is 24 greater than 16? Well, it sure is. And so we get that our base case is checked. Awesome. So now for the assumption. We'd like to assume that there will be a natural number k, which is greater than or equal to 4, such that k factorial is going to be greater than or equal to 2 to the power of k. And I would like to use that assumption to prove the statement of our inductive step, which is that in our inductive step, which is that k plus 1 factorial is supposedly greater than or equal to 2 to the power of k plus 1. Also, so how can we do this problem right there? Well, we see one thing. We can rewrite k plus 1 factorial as k factorial multiplied by k plus 1. And also, we can rewrite 2 to the power of k plus 1 as 2 to the power of k multiplied by 2. Okay, so by our inductive assumption right there, we know that k factorial over here is greater than or equal to the power of k right there. But also, notice one more thing. What we do when kind of changing from k to k plus 1 in our inductive step is we multiply the left hand side, so we multiply the k factorial by k plus 1, by the factor of k plus 1. So this side right there grew k plus 1 times. K plus 1 times. However, the right hand side, so 2 to the power of k, grew only twice. We only multiplied it 2 times, getting from 2 to the power of n to 2 to the power of n, to the power of k to the power of k plus 1. And so if k factorial was greater than or equal to the n before, and we multiplied it by even a bigger number that we multiplied 2 to the k by, well, it has to still be greater or equal to n. Because, well, k plus 1 is at least 5, because k is at least 4. And so k plus 1 is at least 5. And, well, 5 is sure greater than 2. It's not even greater than or equal to. It's strictly greater than 2. And so this, ladies and gentlemen, is the proof of our hypothesis and the end of our induction. I would like to show you guys one more example of using induction to solve inequalities. However, I'm not going to be doing that, but my friend right over there is going to do it. He's going to be doing that for me. So mate, would you mind please? Absolutely mate, there will be no problem for me. Okay guys, so for the next problem I would like to prove that 2 to the power of n is going to be greater than or equal to n squared for all n's that are greater than or equal to 4 and also our integers, so our natural numbers greater than or equal to 4. We'd like to do this one by induction, and so let's first of all consider the base case. So as business as usual, the base case comes first. What's the first number in the set we are operating on? That's 4, and so n is equal to 4 is going to be our base case scenario. For n equal to 4, we're going to get that supposedly 2 to the power of 4 is going to be greater than or equal to 4 squared. Well, that's 16 greater than or equal to 16. 16 is 16, so that's definitely a checked base case right over there. So now for the assumption is going to be definitely not surprising. I would like to assume that there will be a k such that 2 to the power of k is going to be greater than or equal to k squared. Okay, perfect. So now what we can do is use the assumption to conduct the inductive step. Well, that is not quite a circle. So for the inductive step, I would like to prove that 2 to the power of k plus 1 is going to be greater than or equal to k squared. And what I would like to do here is use the same technique we used in the previous problem. So I'd like to compare by how much each of those sides of this inequality grew. By what amount? This time I'm not going to be multiplying stuff because, well, no, oh sorry, I should have put k plus 1 squared here. Okay, I'm not going to be checking by how much I multiplied both sides by changing k to k plus 1. I would like to see how much I added to both sides when changing k to k plus 1 in this example. And so, well, I see that when I change 2 to the power of k to 2 to the power of k plus 1, what I did is I actually added 2 to the power of k, because 2 to the power of k plus 2 to the power of k is actually, oh, that's not quite a k, that's not quite a k either, is actually equal to 2 to the power of k plus 1 because it's 2 times 2 to the power of k. Awesome. What about k plus 1 squared? Well, k squared plus 2k plus 1 is equal to k plus 1 squared. And so I see that I added 2k plus 1. That's really perfect. So what we can do now is we can just go on and compare the things we added, so 2k plus 1 and to the power of k, to see if maybe my left hand side, so 2 to the power of k, grew by a larger amount than the right hand side. Well, that would definitely imply the problem. So let's try and do it. We would like to prove that 2 to the power of k is greater than or equal to 2 times k multiplied by 1. We can still use our assumption though, because, well, that's still the proof under the induction step. So what I would like to do here is use the assumption that 2 to the power of k is greater than or equal to k squared. And we write my inequality as 2 to the power of k is greater than or equal to k squared, which is greater than or equal to 2 to the power of k plus 1. If I manage to prove this inequality right there holding, well, I will prove the entire problem holding. Awesome. So let's try and do it. We'd like to prove that k squared is greater than or equal to 2 times k plus 1. And so let's just subtract 2 times k plus 1 from both sides of this inequality. What we're going to get is k squared minus 2 times k and minus 1. Well, that looks like an incompleted square. So let's maybe try and add 2 to both sides of this equation. That's going to give us k squared minus 2 times k and minus 1 plus 1 greater than or equal to 2. And well, what is this guy right there? This is k minus 1 squared. So we would like to have k minus 1 squared greater than or equal to 2. And for what values of k is it true? Well, definitely for all of the values of k that are greater than or equal to 5. No, sorry, greater than or equal to 3. Yeah, that's awesome. So for the values of k that are greater than or equal to 3, I mean, I'm only talking about integers because if you were to, go about it in real numbers, it's going to be definitely just k greater than or equal to the square root of 1 plus 1. However, the integer that is above it is 3, so I'm going to just say that k is greater than or equal to 3 because k is an integer. And well, if our inductive step holds for all of the k's that are greater than or equal to 3, and also we know in our problem that n is supposed to be greater than or equal to 4, well, pretty perfect, because it means that our statement has been proved by induction, and we can put this beautiful box filled with goodies right there, right now. Okay, so I would like to show you guys one more problem, and one more example of using induction to solve stuff. However, I think for that one, I would like to sit down. Okay guys, so we would like to prove this statement this time. So we'd like to prove that 1 plus a half plus a quarter plus dot dot dot, and we are gonna be summing stuff up to 1 over the nth power of 2. We'd like to prove it's gonna be less than 2, let's say, for n's that are greater than or equal to 1 and are natural. Awesome. So we'd like to do this one by induction. Let's first of all try to achieve the base case scenario. So for the base case, what we're gonna get is n is equal to 1, and well, basically just 1 plus 1 over 2 to the power of 1, which is a half, and that's equal to 3 over 2. Is supposed to be less than 2, but that's definitely checked. So our base case is definitely closed. Now let's do the assumption. We would like to assume that there will be a natural number k such that the sum of all of the reciprocals of consecutive powers of 2 up to 2 to the power of k is going to be less than 2. And now I would like to conduct the inductive step. So we would like to prove that 1 plus a half plus dot 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 plus 1 over 2 to the power of k and plus 1 over 2 to the power of k plus 1 is going to be less than 2. Oh, we can't really do that. We really can't do that, because you see, by our assumption we made earlier, this assumption right there, we can only say that this bit right here, so this bit right there, is going to be less than 2. Nothing further. And well, this doesn't really tell us anything, because this thing could have been, I don't know, less than 2, but now that we've added 1 over 2 to the power of k plus 1 to it, it might no longer be less than 2. So it's kind of, well, crappy, what you say. But, well, does it mean that our statement is false? You see, consider another statement. Let's say I would like to prove that 1 plus a half plus dot dot dot, we're going to be summing up those reciprocals of consecutive powers of 2 once again. I'll have to say now it's equal to 2 minus 1 over 2 to the power of n. Okay, so let's try and prove this one. Let's say for n's that are greater than or equal to 1. Yeah, lovely. So what we're gonna get is, well, first of all, the base case. So that's gonna be, well, 1 plus a half for n is equal to 1 is equal to 2 minus a half. Well, that's 3 over 2 is equal to 4 over 2. That's probably right. Okay, awesome. So let's try and make an assumption. Let's say that there will be a k such that 1 plus a half plus dot dot plus 1 over the reciprocal of d to the power of k is going to be equal to 2 minus 1 over 2 to the power of k. And now the inductive step. Man, I just sore throat. Kill me. So inductive step. We're gonna get that 1 plus a half plus dot 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 plus, we're gonna be summing stuff up to the reciprocal of the k power of 2, and then add that reciprocal of the k plus first power of 2. We would like to prove it's supposedly equal to 2 minus 1 over 2 to the power of k plus 1. Okay, so well, using our assumption we made here, we can say that this bit right there is, going to be equal to 2 minus 1 over 2 to the power of k. Okay, so you can pretty much just rewrite the entire statement here. No, sorry, I wanted the white color. So we can just write the entire statement here as 2 minus 1 over 2 to the power of k plus 1 over 2 to the power of k plus 1 is supposedly equal to 2 minus 1 over 2 to the power of k plus 1. But what is 1 over 2 to the k plus 1 over 2 to the k plus 1? We'll just bring those two to the common denominator, and you will see, guys, that those two things are actually equal to each other. So what we are actually getting here is that this statement is true. Okay, but well, if the sum of all of the reciprocals of consecutive powers of 2 up to some nth power of 2 is equal to 2 minus 1 over 2 to the power of n, well, this means that the sum of all of the consecutive reciprocals of the powers of 2 is going to be less than 2, because, well, 2 minus something is strictly less than 2. So it turns out that our original statement, the one right here, was actually true. It was actually a proper statement. So why we couldn't prove it by induction? You see, this is the paradox of induction. So there are statements that are not too difficult, that are not impossible to prove. They are too weak to be proven by induction. And what we did by changing the inequality sign to the equality sign here, and by proving this equality instead, we sharpened the statement, we made it stronger, we strengthened it. So, we strengthened it. I really hope I'm saying it correctly, guys. So, this is a stronger statement we did here. We proved a stronger statement that also implies the weaker one. And so sometimes, unfortunately, some proofs by induction will require you to sharpen a statement that is just too weak to be proven by itself. And now, guys, I would like to show you two proofs that require sharpening the statement using induction. Okay, guys, so problem number 4. We would like to prove, once again, that the product of a half times 3/4, I'm going to be just kind of multiplying stuff, until we get to 2 times n minus 1, so well, that's going to be an odd number, all over 2 multiplied by n. And we would like to prove it's going to be less, strictly less than 1 divided by the square root of triple the n, for n's that are greater than or equal to 1. Okay, perfect. So we would like to do this, yeah, well, you guessed it, by induction. So first we would like to achieve the base case scenario for this problem. Well, was the first number in the problem's domain, let's say. Well, that's going to be n is equal to 1. So the first number we would like to prove the problem for is going to be n equal to 1. So we would like to now, well, get this thing right there. What is value for 1? Well, for n equal to 1, this is going to be 2 times 1 minus 1, which is going to be a 1. So 1 over times 1, which is 2, is supposed to be strictly less than 1 over the square root of triple the 1, so 1 over the square root of 3. It doesn't feel true because, well, the square root of 3 is strictly greater than, is strictly less than 2, and so there's the... and so the reciprocal of the square root of 3 is going to be less than the reciprocal of 2, because the denominator would be greater for the case where 2 is below the division line. Whatever. So now what we would like to do is make an assumption such that there will be a natural number k for which the product from a half and 3/4 up to 2 times k minus 1 all over 2 times k is going to be less than 1 over the square root of 3k's. And for the inductive step, we would like to, well, first of all, write the entire thing in terms of k changing to k plus 1. So up to 2 times k minus 1 all over 2 times k, and then we just multiply this entire thing by 2 times k plus 1 all over 2 times k plus 2. That's supposed to be strictly less than 1 all over the square root of 3 times k plus 3. Lovely. That's our inductive step to prove. Well, you see, a pretty much awful thing here is that, well, just look how those two sides of our inequality changed. So, well, first of all, this guy right there got smaller, yeah, because the denominator increased because we added that 3 here under the square root. However, on the other hand, this guy right there, well, also decreased, and we can't really compare by how much. Compared to the right hand side, it's just, well, all awful, honestly. And our assumption isn't really telling us anything, because the only thing we know is that this thing right there is going to be less than 1 over the square root of 3 times k, which is larger than the bound we have here. It just doesn't really work out, yeah? And actually, we can, you know, like, try or something, and we can just try to use the assumption and just plug it in here, yeah, to see what we're going to get. So what we're going to get is, well, 1 over the square root of 3k, let's say, multiplied by 2 times k plus 1 all over 2 times k plus 2. It's going to be strictly less than 1 over the square root of 3 multiplied by k and plus 3. Yeah, so that's all we actually can get from our induction, from our assumption. So now let's just divide everything by the reciprocal of the square root of 3 times k, and just let you know, yeah, do this thing. I wanted to square, but I guess I'm not gonna be skipping this step here. So let's just do this, get this square root of 3k to the right hand side, and divide it by the square root of 3 times k plus 3. Awesome, perfect. So what I would like to do now is, we'll just go on and square both sides of it, to get rid of those awful square roots, which I just honestly hate. Okay, so what we are getting here is, well, let's just cancel out those 3's. There's gonna be k all over k plus 1 is greater than 2 times k plus 1 all over 2 times k plus 2, everything squared. Okay, let's try and work this. Let's try and work this stuff out. So it's going to be 4k squared plus 4k plus 1, everything divided by 4k squared plus 8k plus 4. It's going to be less than a k divided by k plus 1. Now let's go on and multiply this stuff out. What we're going to get is, honestly, I just hate multiplying binomials. Binomials and polynomials is awful. So 4 times k cubed. You can skip this part. I mean, you're absolutely free to skip this part. It's just mentally training. Nobody likes it. It's awful, and I hate it. Okay, so this thing is supposed to be less. I mean, strictly less than. Well, now by k, that's not gonna be so bad. 8 times k squared plus 4 times k. Yeah, lovely. So are we gonna be cancelling out those 4k's for sure, those 8k squares, this 4k, and what we are getting here is k plus 1 being less than 0. Oh. Shit. Man. This is definitely not true, because k is, well, at least 1, so that's at least 2, so 2 is definitely not less than 0. So does it mean that our statement is basically just wrong? Does it mean it's, well, absolutely trash and we shouldn't be trying to prove it? No, it means it requires sharpening a little bit. So let's try and sharpen it. So what we see is that everything kind of screwed up, let's say right over here. Yeah, so at this point we see that, well, now when we just kind of multiplied out those polynomials here, everything got messy and we got this absolutely awfully stupid requirement at the very end. Okay, so let's maybe try and do something about this step right there. Let's maybe, oh, maybe I will write it right here. Yeah, so we are at this step where we have 2k plus 1 all over 2k plus 2, everything squared. That's going to be less than 3 times k all over 3 times k plus 3 plus, plus 3. Went too fast there. Okay, so, well, I would like to, let's say, change this part a little bit so that maybe it will work out, well, kind of differently to this thing right there. So I would like it to actually work out in such a way that I will get what I want, yeah? So how can I modify, well, either one of those to get what I want? Well, let's maybe try and prolong this division line here, and let's add an a both at the very top of the equation and at the very bottom of the equation. Maybe we will be able to find such an a that after, well, multiplying all of those awful polynomials, we will actually get something that will work out. And well, I'm just about too lazy to do it right now, and let's just say I will bring on an animation of multiplying all of this stuff right now. So yeah, you have it right there. I hope you enjoyed. Awesome. So as you can see, the a we are getting is a is equal to 1, and this will for sure work out. So what we'll get is that when we say that a is equal to 1, this statement will actually hold. So let's modify our original statement to say that we would like to prove that, well, a half multiplied by 3/4, and we are just going to be multiplying stuff up to 2 times n minus 1 all over 2 times n is going to be less than 1 over the square root of 3n plus a, but a we set to be 1. So 1 over the square root of 3n plus 1. Well, by the animation you just saw, so by all of those, all of that awful binomial multiplication, we're gonna see that when we check the base case here, which will hold, and after we make an assumption, the inductive step will actually hold. And so we actually got this guy right there proven by induction. So this is true by induction. Awesome. And why is that so? Because see, we know that a half multiplied by 3/4 multiplied by all of the stuff until 2 times n minus 1 all over times n is less than 1 over the square root of 3n plus 1 by our inductive proof. However, what is greater than the 1 over the square root of 3n plus 1? 1 over the square root of just the triple n. So we see that by making our statement sharper, we managed to prove the original one. Because 1/2 times 3/4 up to 2 times n minus 1 all over 2n less than the reciprocal of 3 times the square root of 3 times n was actually our original statement we're supposed to prove. Magic. Okay guys, so problem number 5. Okay, so, well, we would like to prove this time that, let's say we would like to prove that 1 over n plus 1, 1 over n plus 1, plus 1 over n plus 2, and we're going to be just summing stuff up until we get to 1 over n plus n, which is 2 times n. We'd like to say is always strictly less than 1 for n's that are greater than or equal to 1. I'd like to do this one by induction. Awesome. So first of all, we'd like to achieve the base case. Well, what's the first element of this that we're trying to prove the statement on? Well, that's definitely n equal to 1. So first of all, we will check the base case for 1. So when I get, well, 1 over 1 plus 1, and that's actually also the last element. So well, that's going to be 1 over 1 plus 1. That's equal to 1 over 2, and this definitely is strictly less than 1. So we have our base case checked, and awesome, lovely. So now for the second part, we would like to assume that there will be a number k somewhere in the set we're trying to prove this statement on, such that 1 over k plus 1 plus 1 over k plus 2, 1 over k plus 2 plus dot dot I'll be summing stuff up to 1 over 2 times k is less than 1. Lovely. And now for the inductive step, now for the inductive or induction step, however you please, however calling it pleases you. No, I can speak English. Inductive step. Awesome. So inductive step. We would like to say that the segment holding for k will imply the segment holding for k plus 1. So now, how will this statement even look like for k plus 1 being the n? Well, first of all, the first guy right there is going to disappear. Why? Because k plus 1 is going to turn into k plus 2. So 1 over k plus 1 is going to become 1 over k plus 2. Then we're going to get 1 over k plus 3. And then we're going to be just summing stuff until we get to, well, let's say, I will just write down a couple of those last terms. So 1 over 2 times k, and then 2 more. So 1 over 2 times k plus 1. And we are finishing with 1 over 2 times k plus 2. So we'll double the k plus 1. And we'd like to prove it's less than 1. Why is this a shitty situation to be in, guys? Because you see, the sequence right here, oh, I wanted to use purple, okay, because the situation right there, well, the sequence here is increasing. Why is it increasing? Because, well, let's say that this sequence here from our segment, we will call it x sub n. And I would like to say that this thing right here is going to be our x sub k, and so analogously this thing over there is going to be our x sub k plus 1. Yeah, so x for n being equal to k plus 1. You see, if we were to go on and subtract right now xk from x sub k plus 1, what we're gonna get is, well, 1 over n plus, 1 over k plus 2, all of that stuff, plus 1 over 2 times k plus 1 over 2 times k plus 1, and also 1 over 2 times k plus 2, everything minus 1 over, that's not a straight line, 1 over k plus 1 minus minus 1 over 2 times k. So just subtracting all of that stuff and, well, simplifying the terms, when I get that is equal to 1 over 2 times k plus 1 plus 1 over 2 times k plus 2. And because, well, there is no 1 over k plus 1 here at the very beginning of the x sub k plus 1 progression, we will get that negative 1 over k plus 1. And, well, the awful thing is that this thing right there is actually equal to 1 all over 2 times k plus 1 multiplied by 2 times k plus 2. And I actually believe I did I unfortunately have to multiply it by hand in the previous video, but because I did, I don't have to do it now. Well, this, for k's that are greater than 1, this is definitely greater than 0. Well, what does it mean? Well, we have a sequence and the latter element is greater than is greater than the former. Got an English error there for a moment. Well, it means that our sequence is increasing. That means every single one of our new numbers in the sequence is going to be greater than the previous ones. Well, that's shitty. Why is it so? Because now, as we've increased the variable for which we compute our series, the series increased. And so, okay, for x sub k, it might have been still less than 1. But now that we've actually added this, it might not be. So how are we supposed to prove it? We do sharpen the statement. That's what we're here for. Okay, so how do we sharpen the statement here? There is a neat trick to be done. So let me use the pink color because it's just perfect color for tricks. So, trick. trick. We would like to create ourselves a new sequence. We will call that sequence y sub n. Some sequence of, well, numbers. And this sequence I would like to be equal to our sequence. However, hope this wouldn't be any fun if I didn't add anything. I would like to add a function f taking in our n's. Function f taking in our n's. With this restriction, I would like f to be only taking in integers, and let's say positive integers, and only spitting out positive real numbers. So it can't spit out any negatives. So I know that this plus sign will never turn into a negative sign. I know that this thing is always greater or maybe equal to xn. It cannot be less than xn. Yeah. However, I would like to make one more thing. So this is gonna be my first, let's say, caveat. Now the second caveat is gonna be that yn is decreasing. Or maybe not decreasing, is non-increasing. What does this mean? Well, it means that if I get yn and I will subtract y sub n plus 1, is going to be greater than or equal to 0. So that all of its terms are equal, all those terms are decreasing at some rate. Yeah? And if we manage to find... Okay guys, so getting back to it, we would like yn to be a non-increasing series, a non-increasing progression, so that the y sub n is going to be bigger than y sub n plus 1 for every single n. Okay, awesome. So we would like to find a sequence y sub n which will satisfy our conditions. Okay, so how do we do that? Well, let's try to find the function f that will actually, well, satisfy the condition that it only takes in integers, it only spits out positive real numbers, and that it will form with xn this kind of a beautiful non-increasing sequence. Awesome. So, well, we're gonna use all of the stuff we wrote right there. So, you know that yn is a non-increasing sequence, so we know that yn minus yn plus 1 is gonna be greater than or equal to 0. However, what is yn? Well, yn is xn plus f of n. What is y sub n plus 1? Well, that's going to be x sub n plus 1 minus fn plus 1. Minus because we are subtracting it, so I'm just distributing that negative sign here and here already. Okay, that's going to be greater than or equal to 0. So what does that thing actually mean? Well, that means that f of n minus f of n plus 1 is going to be greater than or equal to xn plus 1 minus xn. However, we know what is xn plus 1 minus xn because we checked it right over here. X, well, actually that's k, but, well, let's just switch n to k, that doesn't really matter. So xn plus 1 minus xn is going to be 1. It's going to be 1 all over 2 times n plus 1 times 2 times n plus 2. So let's just go on and plug it right here. Getting f of n is going to be greater than, f of n minus f of n plus 1 is going to be greater than or equal to 1 divided by 2 times n plus 1 multiplied by 2 times n plus 2. Lovely, perfect. Well, the nice thing is that we can actually go on and, well, let's say split this fraction in half, because we can either use partial fractions, but I don't know if you know calculus, probably not, and we are going to be covering that actually, yeah, but not now, not in this episode. Or you can just kind of see, this is a bit tricky, that fn minus fn plus 1 is going to be greater than or equal, I'm just writing this thing, and this thing on the right hand side is going to be equal to 1 all over 2 times n plus 1 minus 1 over 2 times n plus 2. Well, why is that? So just, well, bring those to the common denominator, you're going to see that those two are actually equal to each other. That's pretty neat. Okay, lovely. So what we are looking for a function that will decrease at a rate similar to 1 over n plus 1, for example. Okay, so what's the best candidate for that kind of function? Well, I would opt for something like f of n may be equal to, let's say, some k all over n. And we're just gonna figure the k out. Okay, so let's go on and plug this thing into here, getting k over n minus, well, k over n plus 1 is gonna be greater than or equal to, well, 1 over 2 times n plus 1 minus 1 over 2 times n plus 2. I mean, by the way, this step here was not necessary. It just made it a little bit more clearer why I chose this function right here to be our f of n. Okay, lovely. So now we will kind of use the fact that this thing right there is actually supposed to hold for every single value of n there is, and we know that n is at least 1. So let's just plug in this value of n. I don't really care about it, honestly. So I just say that n will be equal to 1 here, getting k minus k over 2 is going to be greater than or equal to, well, a third minus a quarter. A third minus a quarter is going to be 4, 3, and 2 twelfths. There's going to be 1 over 12, 1 over 12. There's going to be, well, k being greater or equal to 1 over 6. Pretty neat right there. Lovely. So if k is greater than or equal to 6, 1 over 6, let's say this. Let's just take k equal to 6. So we are getting that f of n is equal to 1 over 6 multiplied by n. F of n is equal to 1 over 6 multiplied by n. Lovely. So, well, we managed to find such an f, such that our sequence yn, which is equal to xn plus f of n, which is 1 over 6 times n, is going to be a non-increasing sequence. That's definitely awesome right there, guys. I am gonna kill that camera. So, guys, we got what our y sub n x. That's xn plus 1 over 6 times n. So now let's try and prove the sharpened statement. So we'd like to, let's say it's gonna be our assignment to prove that yn is gonna be strictly less than 1 for n's that are greater than or equal to 1. So first of all, the base case. So the base case is gonna be, well, the first number in this set we're operating on, that's gonna be 1. So for 1, what we're gonna get is, well, y of 1, which is equal to x sub 1, y sub 1, which is equal to x sub 1, plus, well, f of 1, let's just write that way, is gonna be equal to a half plus 1 over 6. What is a half and a 6? And a sixth? Well, it's gonna be 8 over 12. Is it less than 1? It is strictly less than 1. Perfect, awesome, love it. So now let's make the assumption. So the assumption right over there, we would like to assume that there will be a k such that y sub k is gonna be less than 1. And now there's absolutely nothing more pleasing than seeing the inductive step right now. And why is it so? Because y is a non-increasing sequence. So we know that y sub k plus 1 is going to be less or at most equal to y sub k. However, what is y sub k? It's less than 1. Ha! And so it's less than 1. And so we see that y sub k plus 1 is also gonna be less than 1. And guess what y sub k plus 1 is greater than or equal to? Huh? xn. I mean, sorry, x k plus 1 actually. So we proved, let me switch to purple again. So we proved that y sub n is strictly less than 1. However, we know that xn is less than or equal to yn, which is less than 1. And so we know that xn is less than 1. And this, ladies and gentlemen, is exactly what we were asked to prove right here. And this is the end. Oh. This is the end of the proof. Love it. Okay guys, so I really hope you enjoyed this bit. I really hope you enjoyed the new format. I mean, I hope that you enjoyed the new format on this channel. If you do, please like and subscribe. I absolutely love you. I love you guys. And that was a drum roll or something. Yeah, so see you in the next one. Bye.